Quantum Mechanics Primer. Wave-particle duality. Wave-particle duality is a fundamental concept in quantum mechanics that describes the dual nature of particles and waves. It states that particles, such as electrons or photons, can exhibit both wave-like and particle-like properties, depending on the experimental context. In this section, we will explore the wave-particle duality in depth, including the mathematical formalism and experimental evidence supporting this concept. At the heart of wave-particle duality is the famous double-slit experiment. In this experiment, a beam of particles, such as electrons or photons, is directed toward a barrier with two small slits. When observed, the particles behave as discrete entities, creating two separate patterns on a screen behind the barrier. However, when the particles are not observed, an interference pattern emerges, similar to what is observed with waves. This experiment demonstrated that particles have wave-like properties and can interfere with themselves. The mathematical formalism that describes wave-particle duality is based on the concept of a wave function, often represented by the symbol psi. The wave function contains all the information about the particle's state, including its position, momentum, and energy. According to the Schrödinger equation, the wave function evolves over time, governed by the Hamiltonian operator. The Schrödinger equation can be described as follows: I times reduced Planck's constant times the partial derivative with respect to time of the wave function of the particle equals the Hamiltonian operator applied to the wave function of the particle. Here, the reduced Planck's constant is a fundamental physical constant. The wave function of the particle represents the state of the particle, and the Hamiltonian operator represents the total energy of the system. The wave function is a complex-valued function that allows us to calculate probabilities of various outcomes. The probability density function, often expressed as the absolute square of the wave function, gives the probability of finding the particle at a particular position at a specific time. The square of the wave function represents the probability distribution of the particle. One of the key phenomena that illustrate wave-particle duality is diffraction. When a wave encounters an obstacle or a small opening, it undergoes diffraction, resulting in the bending and spreading of the wave. Similarly, particles exhibit diffraction when passing through narrow slits, indicating their wave-like behavior. Diffraction patterns can be observed with electrons, protons, and even large molecules, emphasizing the wave-particle duality at various scales. Another phenomenon that supports wave-particle duality is particle-wave interference. Just like waves can interfere constructively or destructively, particles can also exhibit interference patterns. This was demonstrated in the double-slit experiment, where particles create an interference pattern on the screen when not observed. Interference occurs when two or more wave functions overlap, leading to the amplification or cancellation of amplitudes. The uncertainty principle, proposed by Werner Heisenberg, is closely related to wave-particle duality. It states that there is an inherent limit to the precision with which certain pairs of physical properties, such as position and momentum, can be known simultaneously. This principle arises from the wave-like nature of particles, as their position and momentum are represented by wave functions. To visualize wave-particle duality, a commonly used diagram is the de Broglie wavelength. According to Louis de Broglie, every particle, regardless of its mass, has an associated wavelength given by the equation lambda equals Planck's constant divided by the momentum. Here, lambda is the de Broglie wavelength, Planck's constant is a fundamental physical constant, and the momentum is the product of the particle's mass and velocity. This equation relates the particle's wave-like behavior to its momentum. In conclusion, wave-particle duality is a fundamental concept in quantum mechanics that describes the dual nature of particles and waves. The mathematical formalism of quantum mechanics, including the wave function and the Schrödinger equation, allows us to model and understand this duality. Experimental evidence, such as the double-slit experiment, diffraction, and interference patterns, supports the existence of wave-particle duality. Understanding wave-particle duality is crucial for comprehending the behavior of particles at the quantum level and forms the foundation of quantum mechanics. Quantum superposition and entanglement. Quantum superposition and entanglement are two fascinating phenomena that lie at the heart of quantum mechanics. In this section, we will explore these concepts in detail, discussing their mathematical formalism, experimental evidence, and implications for information processing and quantum computing. Quantum superposition refers to the ability of quantum systems to exist in multiple states simultaneously. Unlike classical systems, which can only be in one definite state at a time, quantum systems can be in a state that is a linear combination of two or more distinct states. Mathematically, we represent this superposition using a linear combination of state vectors. Here represents the quantum state and N represent the basis states. The coefficients and are complex numbers that determine the probability amplitudes of the system being in each state. A key feature of superposition is the ability to interfere. When two or more superposed states overlap, their probability amplitudes can interfere constructively or destructively, resulting in interference patterns. This interference can be observed in various quantum systems, such as interferometers and atom interferometry. Entanglement, on the other hand, is a phenomenon that occurs when two or more quantum systems become correlated in such a way that the state of one system cannot be described independently of the others. Entangled particles exhibit a unique type of correlation that goes beyond classical correlations. Consider a pair of entangled particles, often referred to as qubits in quantum computing. The state of the combined system cannot be expressed as a simple product of the individual states. Instead, the entangled state is described by a joint state vector. The joint state vector can be described as follows. The state of the system equals alpha times the state where both qubits are 0 plus beta times the state where both qubits are 1. Here, the state where both qubits are 0 and the state where both qubits are 1 represent the joint states of the two qubits. The coefficients alpha and beta determine the probability amplitudes of the system being in each joint state. Entanglement can lead to remarkable properties, such as non-locality, where the state of one entangled particle instantaneously affects the state of the other, regardless of the distance between them. This phenomenon was famously described by Einstein, Podolsky, and Rosen in their EPR paradox paper. Experimental evidence for entanglement has been obtained through various tests, including the violation of Bell's inequalities. These tests demonstrate that entangled particles exhibit correlations that cannot be explained by classical theories and require a quantum mechanical description. Quantum superposition and entanglement play a crucial role in information processing and quantum computing. Superposition allows for parallel processing, as quantum systems can simultaneously explore multiple computational paths. Entanglement enables the creation of quantum gates and quantum circuits, which are the building blocks of quantum algorithms. To visualize quantum superposition and entanglement, diagrams such as block spheres and circuit representations are often used. The block sphere provides a geometric representation of the state of a qubit, where each point on the sphere corresponds to a unique quantum state. Circuit representations show the flow of quantum information through a series of quantum gates and operations. In conclusion, quantum superposition and entanglement are fundamental phenomena in quantum mechanics that go beyond classical descriptions. Superposition allows quantum systems to exist in multiple states simultaneously, while entanglement leads to correlations that defy classical explanations. These concepts have been experimentally verified and have significant implications for information processing and quantum computing. Quantum operators and observables. In quantum mechanics, operators play a crucial role in describing physical quantities and their corresponding observables. In this section, we will delve into quantum operators and observables, discussing their mathematical formalism, properties, and significance in quantum theory. Quantum operators are mathematical entities that represent physical quantities, such as position, momentum, and energy, in the language of quantum mechanics. These operators act on the wave function of a quantum system and yield observable quantities when applied. One of the fundamental operators in quantum mechanics is the position operator, which corresponds to the position of a particle. The position operator acts on the wave function, transforming it into the position eigenstate representation. The position operator acting on the wave function equals the position value times the wave function. Here, the position value represents a specific position, and the wave function is evaluated at that position. The position operator allows us to calculate the expectation value and uncertainty of the particle's position. Another essential operator is the momentum operator, which represents the momentum of a particle. The momentum operator acts on the wave function, yielding the momentum eigenstate representation. The momentum operator acting on the wave function equals -I times reduced Planck's constant times the partial derivative with respect to position of the wave function. Here, reduced Planck's constant is a fundamental physical constant. The momentum operator allows us to calculate the expectation value and uncertainty of the particle's momentum. Operators in quantum mechanics can also have eigenvalues and eigenstates. The eigenvalue equation for an operator is given by the operator acting on an eigenstate equals the eigenvalue times the eigenstate. Here, the eigenstate is associated with a specific eigenvalue. The eigenstates of an operator form a complete set, and any wave function can be expressed as a linear combination of these eigenstates. Observable quantities in quantum mechanics correspond to the eigenvalues obtained from the measurement of operators. When an observable is measured, the wave function collapses into one of its eigenstates, and the measurement yields the corresponding eigenvalue. Hermitian operators, which are self-adjoint, play a significant role in quantum mechanics. Hermitian operators have real eigenvalues and orthogonal eigenstates. They represent physically meaningful observables, such as energy or angular momentum. The commutation relation between operators is an important aspect of quantum mechanics. The commutator of two operators measures how these operators interact. The commutation relation is described as follows. The commutator of two operators equals the product of the first operator and the second operator minus the product of the second operator and the first operator. The commutator provides information about the compatibility and measurability of two observables. If the commutator of two operators is 0, they commute and can be measured simultaneously with arbitrary precision. To visualize quantum operators and observables, diagrams such as matrix representations or Dirac notation are often used. Matrix representations provide a convenient way to express operators as matrices, while Dirac notation represents operators as ket-bra pairs, such as ket-psi-bra-phi. In conclusion, quantum operators and observables are essential components of quantum mechanics. They allow us to describe physical quantities, measure observables, and calculate expectation values and uncertainties. Understanding the mathematical formalism and properties of operators is crucial for analyzing quantum systems and making predictions about their behavior. Quantum states and wave functions. In quantum mechanics, quantum states and wave functions are central to understanding the behavior of quantum systems. In this section, we will explore quantum states, their mathematical representation, and the concept of wave functions. A quantum state describes the complete physical properties of a quantum system. It contains all the information necessary to predict the outcomes of measurements and calculate probabilities. A quantum state can be represented mathematically as a vector in a complex vector space. The wave function is a mathematical function that describes the quantum state of a particle. It is often represented by the symbol psi, and its square modulus gives the probability density of finding the particle at a specific position. The square modulus of the wave function is described as follows. The square modulus of the wave function at a position equals the wave function at that position times its complex conjugate. Here, the wave function as a function of position represents the state of the particle, and the complex conjugate of the wave function represents its counterpart. The probability density is a non-negative real number, and the integral of the square modulus of the wave function over all possible positions is equal to 1, ensuring that the particle is somewhere in space. The wave function can also be expressed in other coordinate systems, such as momentum or energy. In these cases, the wave function represents the probability amplitudes for the particle to have a particular momentum or energy. The wave function satisfies the normalization condition, which ensures that the total probability of finding the particle in all possible states is 1. This condition is expressed as the integral of the square modulus of the wave function over all positions equals 1. The time evolution of a quantum state is governed by the Schrödinger equation. This equation describes how the wave function changes over time and relates it to the energy of the system. The time-dependent Schrödinger equation can be described as follows. I times reduced Planck's constant times the partial derivative with respect to time of the time-dependent wave function equals the Hamiltonian operator applied to the time-dependent wave function. Here, reduced Planck's constant is a fundamental physical constant. The time-dependent wave function represents the state of the particle as a function of position and time, and the Hamiltonian operator represents the energy of the system. Quantum systems can be in superposition states, where the wave function is a linear combination of two or more distinct states. Superposition allows particles to exist in multiple states simultaneously and leads to interference phenomena. In addition to position and momentum, other observables in quantum mechanics, such as spin or angular momentum, have associated wave functions. The wave function of a particle with spin represents the probability amplitudes for different spin states. The shape and behavior of wave functions are influenced by the potential energy landscape in which the particle resides. The Schrödinger equation with a given potential determines the allowed energy levels and corresponding wave functions of the system. To visualize wave functions, diagrams such as probability density plots or wave function plots can be used. Probability density plots provide a visual representation of the distribution of the particle's position in space. Wave function plots show the amplitude and phase of the wave function at different positions. In conclusion, quantum states and wave functions are fundamental concepts in quantum mechanics. They provide a mathematical description of the behavior of quantum systems and allow us to calculate probabilities and make predictions about measurements. Understanding the properties and mathematics of quantum states and wave functions is crucial for comprehending the nature of quantum phenomena.